All right, so we talked about how increasing the partial pressure of a gas will increase its solubility in a liquid. So that was kind of a qualitative thing, more partial pressure, more solubility. We can take a look at it in kind of a numbers perspective. And this comes from Henry's law. And so what Henry's law states is that the gas solubility is directly proportional to the partial pressure of a gas. And so the overall equation is Cg equals K Pg, where Cg is the solubility of the gas. K is Henry's constant. And so this value is different for every different type of gas and a different type of solvent. It's something that you'd have to be given or calculate, something like that. And then Pg is the partial pressure of the gas of interest, right? Not the total pressure of the mixture of the gas, but the partial pressure of the gas. And so sometimes they'll be just straight plug and chug type of problems. They'll give you, two of the variables and ask you to solve for the third. The other type of problems that you'll see are kind of two-part problems, right? So let's take a look at an example of that. So these problems are often two parts. So in the first part of the problem, they'll give you the solubility, Cg, and the partial pressure of a gas, Pg, under variables 1. Right, so at this pressure and this temperature, something like that, or this, whatever. They'll give you a Cg and Pg under set of variables 1, and what you need to do here is you need to find K, the constant. And then in the second part of the question, they'll ask for Cg or Pg under variables 2. Right, so a second set of variables will be given, and so you need to take your K that you found out previously and then plug in to find Cg, Pg. So let's take a look at an example of this. So we'll say if solubility of oxygen, remember that's O2, it's a diatomic gas, is 1.38 times 10 to the negative 3 molar at a partial pressure of 101.3 kilopascals. What is it at 20.7 kilopascals? So you see they give you two different sets of conditions. So you want to start off with your equation Cg equals K Pg. And then we're taking a look at oxygen, right? And so we see that the solubility is 1.38 times 10 to the negative third molar. Remember, that's in units of moles per liter, so it's a concentration unit. So we're talking about solubility, so that makes sense. And then at a pressure of 101.3 kilopascals. So we need to take this number, plug it into our Cg, and then take this number and plug it into our Pg. And so we can reorganize this equation, right? Divide both sides by Pg to isolate K. So then K will equal Cg over Pg. And then the Cg is 1.38 times 10 to the negative third molar. And the Pg is 101.3 kilopascals. And then plug that into your calculator, you get 1.36 times 10 to the negative 5 molar per kilopascal, right? So that's now your value of K. So now you have K. And then notice the question asks, what is the solubility at 20.7 kilopascals? So we have to rewrite our equation here, right? Again, Cg equals K Pg. And now we have our K. So we can take that, plug it right into there. And then we have this 20.7, which is our new pressure. And so we can take that and plug it into this PG. And then, so you'll get CG equals this 1.36 times 10 to the negative 5 molar per kilopascals times the PG, which is now this 20.7 kilopascals, right? The kPa units are going to go ahead and cancel out, and we'll be left with molarity, which makes sense because it's a unit of concentration, and we're looking at the solubility. So plug that in. This is what you'll get. And then that's your answer, right? So there's just one example. Check out your book and your homework for more examples.